Morning, guys. So I'm hoping to finish off the Chapter 2 unit with you today. Over the last 2 days here, we've been looking at electron configuration. Basically, it's a couple modifications to the Bohr model. There's some things that the Bohr model predicts really well, like all those absorption and emission studies. We'll come back to that more in Chapter 3 and Chapter 4 for bonding. But definitely something that's missing in the Bohr model, why it sort of starts failing by about potassium and calcium on a periodic table, is because it really can't capture those inner electrons. Unlike the valence shell being the s and p orbitals, the d orbitals, f orbitals, no matter the crazy shape and whatnot, those are always held much closer to the core, which the Bohr model just simply can't show with these electrons in orbit around the nucleus. Just to finish off the chapter here, basically what I want to introduce is just some experimental evidence. What did we actually do so that we actually concluded the shells can actually be subdivided into floors? Why aren't they all on the same floor? And what sort of data do we have to support it? So just as a quick comparison here, let's just take a look at the carbon atom just for just reference here. So carbon atom here currently has 6 electrons. Right? We'll just start off with the Bohr model. I'm not too worried about the nucleus. First 2 electrons go in the first shell, and the next 4 electrons, watch as I add these electrons here, I add them on single, 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 right? Only until the 5th electron, then we start pairing them. Let's compare that with the energy diagram model. So let's compare sort of which parts match up and which parts don't match up. So far on my energy level diagram, I don't want to draw these circles around. What I'm drawing here is the potential energy, the storage energy for being a certain distance from the nucleus. Energy level 1 is relatively low energy, so I only have the S kind of room, so 1S. Floor number 2 was when I started saying there's going to be a split. So floor number 2 can have either an S kind of room or it can have a P kind of room. Whenever the P kind of room shows up, it always shows up in sets of 3. Right? And then what we did is we off-bought. Right? I add electrons lowest energy first. Where do the first 2 electrons go? Well, given the whole hotel is free, the first 2 electrons will go in. I'm going to go in 1s. I'm going to go in 1s for the other electron. The next 2 electrons will go in 2s1, 2s2. That's actually different from the Bohr model, because for the Bohr model, it actually says when I go single, I add that 6th electron here by itself, when in reality it's actually paired up. So it's already something that's off. We still do the Bohr model single, 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 because it still makes us good predictions in our bonding chapter, but we'll need to come up with a correction term in that chapter. Now, after we fill in the 2s, we're going to fill in the 5th electron. 5th electron goes in your 2p. 6th electron does your Hund's rule, so it goes in single, single. At least that part there is consistent. But what we're showing you here is shell number 2 is actually subdivided onto 2 different floors. So it's trying to mark off here, if I just sort of think more about like an orbital diagram here, these 4 electrons here are not all equal distance from the core. Unlike the Bohr model, which says sort of, yeah, it looks exactly the same. It looks degenerate here. They're definitely not degenerate. The P's are actually higher energy. And in fact, spatially speaking, your P orbitals here, which are those dumbbell shapes, I'm not going to do that too much, but those dumbbell shapes here, those dumbbell shapes are actually farther out from the nucleus than, say, the S electrons are. So if I have, let's say, 2 electrons on a 2s shell, and I have 2 electrons on a 2p shell, this time what I'm going to do is I'm going to come in and I'm going to try to figure out how hard is it to actually remove an electron. Removing an electron off p electrons should be somewhat different from the s, because even if you just come in with a pair of tweezers, you grab the first electron that you see, the p electrons are going to be farther out from the core. They should be a little bit easier to remove than, say, the s electron is. So we're going to use this notion of what's called ionization energy to actually qualify, to get some evidence for these sublevels existing. We will see ionization energy a little bit more in chapter 3, but I just want to introduce this term to you here. Ionization energy, or IE, careful, a couple of technical notes. Yes, we are going to come in with a pair of tweezers. We're always going to pull off electrons, so we're going to become more and more positive. But you want to be careful. This one here is stated as a minimum energy needed to remove an electron. Right? Because if I have infinite amount of energy, I can pull off all the electrons if I want to. I can make up any charges I wanted to. But this is the least energy you can put in to pull off an electron. it turns out if I just do this to one single carbon atom, let's say I pull off the first electron, I'm going to call it here the first ionization energy. So I pulled off the first one here. If the Bohr model are correct and all 4 electrons were equidistant, I would imagine between the first time I do this, the second time I do this, third time I do this, sure, it might gradually get harder, but because they're all equidistant from the core, I would imagine the trend to be fairly linear. It's what I actually see in the trend here that actually qualifies, wait a second. There has to be some sort of sublevels. How come the first 2 were actually easier and then the next one here was harder? I can't really predict that based on the Bohr model. Again, I mentioned here, if you did that to one single atom, the energy value here turns out to be actually be a really tiny number. So what I'm going to do here in the qualifying definition, I actually do this not just to one atom. I line up a whole Avogadro number, and to each atom along the Avogadro number of atoms here, I'm going to pull off that electron. So remove an electron from a mole, and the Avogadro atom here, it could have been solids, liquids. I'm going to choose gases because gases are the easiest to remove those electrons. So I'm going to specify that gaseous species. Species just means substance, chemical, and they have to be at ground state. So you're going to find times that in our definitions, we're going to be really, really technical. We're going to say, yeah, I know I'm just removing an electron, but I would have qualifying things like it's the lowest energy. It's not just doing to one atom, it's a whole mole, and it has to be gas so that I can make a fair comparison, so that if I have tables in my data booklet here, you can match up 2 elements. So what they like doing here is they like asking you write a representative equation. Usually when we think equation, we think math. In this case here, that's not so. A representative equation here is actually just a almost like a balanced equation. What is it before and what is it afterwards? Typically, I'm just going to use M as just a placeholder of any element. Because it does have to be gas, you have to include this gas symbol there. And all we're doing here is this metal here happens to have some number of electrons. I have no idea how many. I have no idea which subshells. I'm just grabbing the first electron that I see, working my way outside to inside, and I pull off this electron. As I remove that electron, you notice I'm not touching the core, so I'm still going to be element M. But because I removed an electron, that electron took away a negative charge, my M is now going to become a positive charge. I can say M plus 1, and then the electron is now actually free to go. That M plus 1, you can either put square bracket here with a charge in the corner, or in this case here I can just put it directly M plus, also is in the gas state. And in that case there, that's your representative equation for your first ionization. For the very first electron that you come in at here, that's making M plus. Just like I showed you earlier for carbon, I can actually do second ionization. So what if I take the M plus from earlier? It is in a gas state. I come back again, you may have sort of another electron, I grab the next electron I see, and now I remove that electron. To remove that electron, this is now called second ionization energy. This is going to be M plus 2 as a gas. I want to show you with these equations, every time you ionize, it is only for one electron at a time. Although we will see second ionization is typically going to be harder than the first, it's not harder because it's cumulative. It's not like, oh, I need to remove 2. Second ionization is just for removing the second one, but the second one is actually harder. Let me put some numbers to this here. Let's say first ionization for a metal, totally made up here, 10 kilojoules per mole. There's that mole restriction there. I line up a whole Avogadro number and I try to pull off the first electron that I see, the easiest electron, P first, then S, then D, then F. Let's say that took 10 kilojoules for going down the line and pulling off the electron. Let's say the other one is actually 100 kilojoules per mole. This is the energy that you need to remove the electron. The lower the number, it means this one here is easier to remove. The higher the number means it's actually harder to remove. And in fact, this usually happens here if I take one atom and I come in and I remove multiple electrons, it's going to end up getting harder and harder. We're going to call these ones here successive ionizations. Successive means one after the other. Successive ionizations become harder, right? What are the reasons here? So harder, we have a higher ionization energy. The reason is because it all comes down to size. We're going to study that a lot more in the next chapter, but it's because the radius decreases. First thing is, why does the radius decrease? Well, what's going to happen is every time you remove an electron, you've now decreased the amount of repulsion between that electron and the remaining electrons here. So one consequence for radius decreases here is because, actually a lot of consequence here. You can say there's less electron repulsion. Okay. You can also refer to the fact here, every time I ionize, it's now become plus because I'm having more net positive charge here. I'm going to pull my leftover electrons even tighter. So I'm actually forming cations. I'm forming increasingly positive charges. The more positive I am, I'm going to hold my shells tighter. In fact, if I lose enough electrons, I might even end up losing a shell. And especially when you lose a shell, you're going to have to reach a lot closer for that next electron. It's also may even have full shell stability. We'll see that in the next example. And this actually became a good evidence for us that we actually have sublevels. So what we're going to look at here is we're going to look at successive ionizations. What I'm going to plot for you here is successive ionizations for the sodium atom. And let's just go straight back to just the Bohr model. So Bohr model, sodium, 2 electrons on the first shell. Then we add those 8 electrons on the next shell. Sodium actually has 3 shells out. That's what it looks like. What I'm going to plot for you graphically, this is done experimentally, I'm going to plot for you the ionization energy. And I'm going to plot it against sort of which ionization I'm doing. So as I go across, it's going to be first time I come for the first electron, second, third, and going on from there. So as we consider doing this experiment here, you come in for the first electron, you grab the outermost electron. This one here is the one that's furthest away from the core. This one here is going to be relatively easy to pull off. That's your first ionization. So first ionization, let's make it some number, right? Some really low number here. So now that's become sodium plus, it's now more positive. It now pulls in the charges a little bit later. It also has lost a shell. So what you're going to notice here is if I come back for an electron on the second time, I'm going to actually need to reach in for one of these inner electrons. That inner electron here is going to be a lot closer to the core. We're going to see there's actually an attraction. The closer things are, the stronger the forces between them. Because I'm having to reach so much closer, it's going to already be much harder. And notice that once you lost that third shell, the inner shell is actually full. This is actually enjoying some full shell stability. It's like your noble gas. It's stable because it already has all the electrons it wants. It doesn't really want to lose this electron. So having said that here, I would imagine that the second ionization here is much harder than the first. In that case there, the second, suddenly there's a jump. As you ionize it a little bit more here, it steadily becomes more and more positive. There's less and less repulsion. So when I come back for a third electron, each time I come back, it's only for 1 electron at a time. The atom shrinks by ever so slightly a little bit every time because we are going to be a little bit closer, a little bit less repulsion between the leftover ones here. Third one here is going to be harder. And in fact, what we end up getting here is more of a sort of zigzag pattern. If this were really the case, where all 8 electrons were all equidistant, I would imagine something linear. I would imagine, okay, third one is harder, fourth one is harder, fifth one is harder, sixth one is harder, right? There's no real deviation. There's no real detail into why one on that shell may be harder than the others. It's actually evidence, if I actually do this experimentally, we'll do a lab on this one here, this graph here actually starts zigzagging back and forth. So although these ones here are all, let's say, shell 2 electrons, it's not a nice linear trend as I might expect. And then what's going to happen here is when I get up to, let's say, the 9th electron, I pulled off 1, I pulled off the 9 there. 9 is sort of the last highest one here. Going to the 10th electron, removing 1 from the inner shell, again, I'm going to be a lot closer to the core. This is going to be significantly harder than those ones. This one here will suddenly jump up again. In fact, we can look for when these sudden jumps occur. A sudden increase in ionization energy, usually that means we've lost a shell. Because when I come back in for another electron, I'm having to reach a whole lot closer to the core. It's a lot harder to remove close to the core. In fact, this ionization energy, if you do this experimentally here, it's so drastic between one shell and another drastic. Usually they plot this on a log scale just to make sure it's not going to be an even scale, like a linear, nicely spaced out scale here, but basically so you can plot all the graphs on. We're going to see a little bit on why there are these little exceptions along the way as we go down. So this sort of introduces one style of question here. So let me give you a few numbers here. successive. Successive again means one after the other. Successive ionizations for X as a gas. I'm going to give you, first time you come in, it's 20. Second time you come in, for that next electron, it's 210. Third electron you come in, it's 3,500. And then fourth electron is 4125. It doesn't have to be a really nice number. So this is coming into an element X. You came in 4 times, you removed 1 electron at a time. We note the trend. We know it steadily gets harder, right? Increasingly hard to remove the electron. What the question is going to ask you is, can you predict which group does this one here belong? Which group does this belong? Now, normally you would know what element it is, so you can just look on the periodic table. How can I use this experimental data to actually predict which group is going to be? Well, again, we saw, although there's going to be usually going to be a steady increase in terms of ionization energy, usually the biggest jump will be between, when I go from shell number 3 to shell number 2, I'm a lot closer. That one is so much harder than the one before it. So that's why I'm going to actually employ in this question here. I don't actually care about these numbers per se. What I care about here is the difference. So this one here, that's about a 190 difference here. This one here, suddenly goes up here. What is that? 3290. Then we're sort of already hard, but going from one to the other, this is only, 625, give or take. And basically what it's saying here is, whenever there's the big jump here, probably I lost a shell, right? Between the second electron and then before I can come back for the third, I probably removed that complete shell. So the third one is a lot closer to the core. I needed 2 electrons before that happened. So maybe an X would have actually had, I don't know exactly how many shells it has, but the first one, relatively easy, 20. Next one, a little bit harder, 210. But then the third one I come in, it's going to have that noble gas configuration on the inside. It's a lot closer to the core. That's significantly harder. So that's why this one here is suddenly jumped higher. I would say this one here belongs to group number 2. It was 2 valence electrons before that happened. We're going to do a lot more with this in chapter 4. You can find your number of valence electrons just based on the group number. And just counting back, you can figure out which group it belongs. That's one way of asking the question. Let me just introduce to you the last way of asking the question here. That was successive ionizations. That was going to one element multiple times. This time what I'm going to do is I'm only going to compare first ionization energies. So this time I'm only coming to each element just once. But what I'm going to compare this time is not just one single element, pull off 1 electron. This time I'm going to pull off 1 electron on different elements. And I'm going to try to get a periodic trend. I'm going to try to get a pattern on the periodic table that as you go to the right on the periodic table or down on the periodic table, what might I expect would happen to the ionization energy? Does it get harder? Does it get easier? We're going to see a lot of trends in chapter 3. A lot of the trends come down to the radius. So a lot of this will be fleshed out in the next chapters. But we can actually do this here. Starting from shell number 1, let's say hydrogen. Hydrogen has 1 shell, right? I don't necessarily know how hard it is to remove that electron, but that's on shell number 1. How does the size of hydrogen compare to the size of lithium? Well, shell number 2 for lithium. Shell number 2 is actually farther out from the core. And in fact, as you keep going downwards, we're just steadily getting more and more shells. You'll notice that because these are all group number 1, these are all going to have 1 valence electrons. More on that in the bonding chapter. But you notice as you go down on the periodic table, so the radius, I'm going to say radii for plural, the radius actually increases down on a periodic table. We call the up and down, we call them families or groups. Radius increases going down a group. In chapter 3, there's going to be a lot of explaining style questions. How do we know the size increases? This one here should be fairly easy. The radius increases because we actually get more shells. If you have more layers to the onion, of course you're larger. And what we're going to find is, as you get larger, does it get easier or harder to remove the electron? Well, when you're larger, the electrons are farther away from the core. We're going to see in chapter 3 here, the closer things are, the stronger the attraction. In this case here, because the nucleus is having a hard time reaching so far out, it's actually going to be easier to actually remove the big atom than from a small atom here. So as the radius increases going down a group because of more shells, we're going to actually see that your IE, your ionization energy, actually decreases. It actually gets to be easier to remove. And again, your justification here is because ionization energy decreases because electrons are less strongly attracted to the nucleus, just because we're farther away. And again, we can do this experimentally. We can take a sample of each of these elements here, and that's exactly what you find in your data booklet. I believe it's section 8. It gives you all the ionization energies. Again, what I'm doing differently here is I'm actually comparing the first ionization energy for all the elements. Now, what about going across? A little bit harder. As you go across, let's take lithium's row here. So we go lithium, next to it is beryllium. Because these are all on the same row on the table here, they actually have not gained a shell. So it's not as obvious what's happened to the size of it. However, what we know is as you step across, we're actually going to pick up another proton, pick up another proton, pick up another proton. As the center of it gets to be a little more positive, this is 3 protons, this is 4 protons, this is 5 protons. As the core becomes more positive, sure, you're also getting more electrons as well. There's going to be some more repulsion as well. But the effect that dominates here is because we're all going to be 2 shells, but my center itself is getting larger and larger, the more positive the center is going to be, you're going to end up pulling in the shells in tighter. We actually see this experimentally when I measure the radii here. I actually see the radii actually steadily drop going across. So again, here's a trend I can list for you here. So we can say the radius decreases. We use a terminology here of across a period. A period means going across a row. We just imply we read left to right. So going to the right, we tend to get smaller because more protons attracts the same number of shells closer. Right? Because as you go across, it's not like you're gaining shells, right? All these will have 2 shells. But as the core itself becomes more and more positive, the electron shells get tighter pulled in. So if that's the case here, I'm coming in and I'm comparing the 1 electron. Is it easier to remove lithium's electron or say fluorine's electron here? Notice this is not a question of, oh, am I metal or non-metal? Do I want to gain or lose electrons? More on that in chapter 3. This is just purely a comparison of size. While the thing is tinier here, electrons that are much closer to the core here are much strongly attracted. So you're going to need to pull even that much harder to actually get rid of this electron. We actually have this sort of inverse relationship. Ionization energy actually increases for that reason. Increases going across. The electrons are more strongly held by the nucleus, so you need to pull even harder. If you like these trends here, you're going to really like the next chapter. We get a lot of explaining style questions, and we're going to find a lot of trends here have to do with radius. So far, just sort of conclude from there here, we find an opposite relationship. Let's say the bigger the radius, whichever way you want to point on the periodic table, the bigger the radius, the lower the ionization energy. These are inversely related, and vice versa is also true. The reason why it is showing up on this chapter, however, is there are exceptions, right? With any rule, there's always things that don't obey the rule. So in this chapter here, we're going to focus on nitrogen and oxygen. Based on what we just said, nitrogen is sitting here, oxygen is right beside it. We would imagine, hey, they're both the same shells, right? Oxygen has 8 protons, it has 1 extra proton. We'd expect nitrogen here to be a larger atom, oxygen here to be a smaller atom. I think that is true. And yet, the question is, can you explain for these 2 atoms, explain why nitrogen has a higher ionization energy than oxygen? Right. So again, let's take it apart here. So far, we know about the size, right? Nitrogen has 7 protons, oxygen is 8. They're both 2 shells. So this guy here has a smaller radius. I would imagine that the electron would be harder to pull off the oxygen because it's tinier. And yet they're saying here nitrogen actually has the higher ionization energy. It's actually harder to pull off nitrogen's electron even though nitrogen's atom is actually larger. So we need to go to configuration to actually explain why this is. Nitrogen has a configuration here, 1s2, 2s2, 2p3. whereas oxygen has a configuration 1s2, 2s2, 2p4. We can draw what's called an arrow and box diagram. It's sort of like an energy level diagram here, where I have the arrows sort of filled in. I'm just drawing sort of from the 2s layer and the 2p's because I have 3 of them, so I have sort of this configuration. If you look at that configuration, why might this one here be harder to remove than this one here? Again, this is one of our exceptions here. They always like asking this one. Well, this one here looks like that exception with chromium. Chromium, remember, it was, oh, I'm just one short of having a half-filled shell. Half-filled gives me some stability. Now, it's not enough to make me any exception like 2s1, 2p4 like we did in chromium. However, we can still use that notion here. Right now, nitrogen is enjoying a half-filled stability. If you remove the electron, it's not impossible, but you actually get rid of that electron. You actually remove from me my half-filled stability. I'm going to resist you from doing this, right? So the reason why it's harder is because you would lose half-filled stability, right? And on the other side here, well, in this case here, you can argue it can gain half-filled stability. That's why I want to look like that. The other thing you want to keep in mind is, although I do squeeze these 2 electrons into the same room together, do these electrons like each other? Well, no. Electrons, they always have negative charge. Were it not for the compromise, will still be closest to the nucleus. I'll be most strongly attracted. There's going to be a lot of repulsion. Having 2 electrons squeezed into that room together, by pulling 1 electron out, I actually can minimize the electron repulsion. There's always going to be competing factors as well. Yes, without a charge, right, there's going to be less charges to actually attract. But again, we want to come up with a reason to justify the trend that they asked for. Right? I do find that exception a little more convincing than the other exception, and we'll end off with this one here. The other exception here, they give you a statement. Explain why boron's electron is easier to remove than beryllium. So they just picked 2 random elements here. If you look at where these are on the periodic table, let's just go off our trend first. Beryllium is sitting right here. Boron is sitting right here, also on row number 2. We would have expected beryllium has less protons, larger atom. Boron has a smaller atom, it has more protons. You want to always translate this for yourself here. What does it mean easier to remove? We know we're talking about the trend ionization energy, the difficulty with which to pull off the electron. Easier to remove actually translates to lower ionization energy. So why does boron have a lower ionization energy when I would expect boron here is a tiny atom? It should be harder, and yet they're saying it's actually lower. Again, the way you explain this is you look at configuration. That's why it's appearing in this section. Can you come up with a reason, looking at these 2, why it may be easier to actually remove boron's electron than beryllium's electron? Well, is it a fair comparison here? In some sense, not quite. Because if I look at an arrow box diagram here, I look at the 2s. This one here is actually, though that one's paired up. This one also has a 2s, that one's paired up. But the electron I'm actually pulling off, remember I'm only pulling off 1 electron, is actually not pulling off 2s in both cases. This one is actually pulling off from a 2p. So a couple things you can say here. The first ionization for beryllium would have pulled off an s electron. You can say an s electron is harder to remove than p. The reason for that is a spatial argument, because if you look at like a 3D coordinate system, the s orbital we drew yesterday, s orbitals here are always spherical. P orbitals as a dumbbell shaped. P orbitals always have a region of the p orbital that's actually a little bit farther away from the core. Because it is actually farther away from the core, it's actually a little bit easier to remove. So our p orbital here, there are parts of the p orbital that are actually further away. So if I came in with a pair of tweezers, because I'm not having to reach as close to the nucleus, if the p orbital were out here, the p orbital is easier to remove than the s. And that's what actually makes the difference. We're actually not playing fair here. I'm trying to pull off the s electron off of beryllium, but I'm actually pulling off a p electron on a boron. P electron is farther out, sort of the same reason out, farther out from the nucleus, so therefore it's easier to remove. Right? So that's why it's showing up here. We're going to do all these trends a lot more detail in the next chapter, but you see you can actually qualify some of these trends based on the configuration stuff that we have done. Remember this for our ion stuff here gave rise to, we pull off P and then S first. It's because P's are the easiest to remove. And again, this is another evidence, even though these are both shell 2 electrons, even though we would expect the trend to be fairly linear between pulling off one and pulling off another for successive ionizations, this is actually going to end up more so if I did like an ionization against your sort of how many times you come back for ionization, you actually get more of a zigzag. Yes, there is a general increase as you go across a period, but there are little kinks here and there. Oh, this one here was actually harder than this one, or this one here is actually harder than that. This one is half filled, and this one is not half filled. So you get little kinks here and there, and because this one here is kink like this, that actually gives you some experimental data that we have sublevels. So that does finish us off for chapter 2. Keep practicing through your quests and your other worksheets there. Let me know if you have any questions. Thanks, guys.